Hey guys, welcome back to another video. Today's video is going to be on graphs for data structure. And for something like graph, it will most likely take up 2 or 3 more videos, depending on how I'm going to organize the things together to put it into the video. So for today, we're just going to learn the most basic thing about graph. And then afterward, I'll write out a code for it and just explain the code, I guess. Okay? And then for here, it would just be like writing the things out and explain what a graph is. Okay, so in a way, let's just ask like the most basic question, right? Why is a graph important? Or like, why do I have to learn this? Okay? So you have to think of it like this. A graph basically shows up everywhere because a lot of the real world stuff is basically things connected to other things, like I've written here. So let's take some examples, right? Social networks, where people are connected by followers or follows. Maps or GPS, where cities are connected by roads. Internet networking, like for example, the computers or routers, they're connected by cables or Wi-Fi. School prerequisite, classes are connected by other classes that you must take before you're able to take this class. Let's see what else, like recommendations, right? User or items are connected by interactions, things like that. So once you understand graphs, you can basically solve like a huge category of problems. Things like shortest path, dependency, connectivity, cycles, and many more. So that's like the question for why do I have to sort of like learn this, or why is it important? And now we have what is a graph. So a graph is a collection of vertices, or you can also just call it nodes. So so nodes, and then we'll say, for example, 0, 1, 2, 3 as the node, right? And then we have edges. Now the edges are basically the connections between the nodes. Connections between nodes, like that. So graphs can be indirect or undirected. Basically, the connection goes both ways. So for example, let's take friend, right? We have friend A and then friend B, or person A, person B. So let's say if A is friends with B, then B is also friends with A, right? That's the undirected. Is basically connection goes both ways. Here, I'll write it out as well. Now we have the other one, which is directed. That means this one is the opposite. The connection is one way. So, let's say this person A follows person B, right, on Instagram, but person B doesn't follow back. That's directed. We also have weighted. So weighted means that the edges have a cost. Okay, there's like a cost in it. This can be distant, time, money. For example, let's take, for example, like a road distant between person A and person B, right? Like they have a distance. That's weighted. Okay? So, and of course, I'll explain what they are with graphs as examples. Let me erase it. Okay, let's do the first one, which is undirected. So let's, for example, given, let's say V equals 5 nodes, and we have 1, 2, 3, 0, 1, 2, 3, and 4. And now we have edges. The edges will be written like this: 0 to 0, 1, 0, 4, 1, 2, 1, 3, 1, 4, 2, 3, And one more. Let's put 3, 4, like that. So what the edges mean, and this is kind of important, right? So for each pair, as you can see, for U and V, it means that the node U is connected to node V, right? And since it's undirected, that means the V is also connected to the U. So when you look at 0, 1, it really just means that 0 is pointing at 1 and 1 is pointing back at 0. If you look at 1, 3, it means that the 1 is pointing at 3 and 3 is pointing back at 1. So when you do the drawing for the graph, it will look something sort of like this. Let's do 0 here. We have the node 0, and we have it pointing at 1, and 1 is pointing at back at 0. Let's do 0 pointing at 4, and it points back at 4, like that. 1 points at 2, and then 2 points it back. And then, 1 points at 3. And you don't have to draw it like the way I'm drawing it. You can draw it however you want. You just gotta make sure that you're actually pointing the node, you know? 1 points at 4, so like this. And then let's say 2 is pointing at 3, and 3 is pointing back at 2, and 3 is pointing at 4, 4 is pointing back at 3. So it looks kind of like that. It looks bad, but I'm trying my best. Not the best drawer, but it's fine. So, and then when you read the drawing like this, right? When you read the drawing, you sort of notice that something like node A is sort of like a hub. Because like it connects to 0, 2, 3, and 4. Whereas like node 0 only connects to the node 1 and node 4. And then node 2 and 3 also connect to like each other, things like that. So you can say that node 1 has many edges. 1, 2, 3, 4. And then node 0 has like less edges, right? Compared to node 1. So it's just 1 and 2 right here. And that's normal in graphs. So and so there's that. And now the thing is, you have ways to sort of like represent a graph. It's not always about like just drawing it. Obviously drawing it out is also good. You can, like for me, if I look at it, it looks pretty good, I guess. So it's sort of like the big idea with like different ways to represent a graph is how do we store it in code, right? So we need to store who connects to who so that later we can like run algorithms such as like BFS and DFS or like shortest path. And there are like a couple of common representation. I'll show like the first three. I'll show like the three of them. And I know, at least from what I've taught, is that the most common one, it will just be the adjacency list. And I think this is the common one. So what it is that for every node, you have to store a list of its like what you call neighbor. So let's say we have node 0, 1, 2, 3, and 4, right? The node 0, what is node 0's neighbor? So it's basically saying what is node 0 pointing at, right? It points at 1 and 4. So you write down 1 and 4. What about node 1? Like I said, node 1 has basically everything, right? So you write it out. 0, 2, 3, 4. What about 2? 2 has 1 and 3. Right here. What about 3? 3 has 1, 2, and 4. And then node 4 has 0, 1, and 3. Like that. And that's how you write it. Or you don't have to write the... You can write an arrow too. That also works. Like that. Okay? So why it's good? In a way, it uses like less memory when the graph isn't super dense. Very fast to loop through neighbors, which is what BFS and DFS are like consistently does. This is basically like the default choice when it comes to like writing out the real code and etc. And so, you know, and this you use it at its best when like when the graph is like sparse or sparse. I think that's how you say it. Basically, not too many edges. Okay, And most of the real graphs don't really have that many edges anyway. So, okay, so that's one of them. One way to write it. We have another one, which is adjacency matrix. And this will be what you call like a 2D table. Okay, so for the same graph, let's have 0, 1, 2, 3, and 4. Right here we'll have the same thing, 0, 1, 2, 3, and 4. It'll look something kind of like this. What we have here is 0, 0, 0, 0, 1. 0 has a 1 here. So 0 is pointing at 1. You give it a 1. When you write it out, it's basically like a zeros and ones, right? So 0 means a no, 1 means a yes. Okay? So is 0 pointing at 2? That's a no. 0 pointing at 3? That's a no. Is 0 pointing at 4? Yes, it is. What about 1? Is 1 pointing at 0? Yes, it is. And let's just use this. I'm using the same graph, but I'm just going to write it here because the graph is all the way up there. Okay, what about 1? 1, 1 is nothing. 1 is pointing at 2. 1 is pointing at 3. 1 is pointing at 4. 2 is pointing at 1. Sorry, 2 is not pointing at 0, but 2 is pointing at 1. 2 is not pointing at 2. 2 is pointing at 3. 2 is not pointing at 4. And then for 3, 3 is pointing at 1, but not 0. 3 is pointing at 2. 3 is not pointing at itself. And then 3 is pointing at 4. 4 is pointing at 0. Pointing at 1, not 2, yes 3, not 4. Now for something like this is, I guess you could call it very easy to understand, right? It basically, it's checking if an edge exists in an instant, pretty much. Let's say you have the question, is there an edge for 2 and 4, right? So when you do like matrix, and then you do 2 and 4, you just check 2 and then 4, and the answer shows you 0. You can check it here, you can check it here, it will show the same thing. They're both 0. And when they say 0, it just means no. Now the thing is now there is a small bad side about this, is that it does use a lot of memory. And usually it's v times v. Okay? So let's say if v is like 10,000, for example, right? Then the matrix is huge, and that's bad. So this is only good if, for example, if the graph is dense, meaning there's a ton of edges, and you consistently need to do like, does the edge exist check. Okay? And then finally, you just have like the edge list, which is simply like the list of edge. And what it is kind of just like this right here. That's how you store it, you know? Now, that means I don't really have to draw much. You just have to look at this. So this is super simple, easy way to basically input format. And a lot of the times, they just give you the edges like this so that you have to draw out the graph yourself. But this is what you call the edge list. Like that. Okay? Great for algorithms such as like the Kruskal, I think that's how you say it, or I don't know if I'm not very good at when it comes to like saying the names, but it's something like this, MST. Okay? Now, there sort of is a downside. It's not great for like neighbor traversal. And then so if you want like neighbor of node 1, then you have to kind of like start scanning the list and check for the ones. Also like we have 1 here, we have a 1 here, we have 1 here, a 1 here, you know? It's not like where, hey, I'm just going to look at the adjacency list and boom, there it is. Oops. Or for example, the adjacency matrix where I can just boom, there it is, or boom, there it is, you know? So yeah, that's basically the downside for it, but it's not that bad. Okay, so for basically everyone, just use the adjacency list, because most graph algorithms are just like for each neighbor, and like the adjacency list just makes that like easy. It just makes it easy and efficient, right? Okay, and then now I'm gonna basically write out the code for you. So, all right, let's begin the Java code to basically build the adjacency list, which is what you call like for the undirected, okay? And so here what we have is we're just gonna import the Java, and we're gonna have so we're gonna first do add an edge basically. I'm gonna keep in mind this is for undirected graph. We have static void add edge. Okay, we're gonna have list integer integer u integer v, close it like this, then get u. Again, I'm gonna do it kind of like the LeetCode way. I'm gonna write it out, and then after I'll explain to you line by line, so don't worry. Then v, then add u. So this is how you add an edge. Next one, what I want to do would be print the adjacency list. So for this, the static void, we're gonna call it, let's call it print graph, right? Same thing, list, integer, jeez. And then for I equals 0, we're gonna write a for loop. I is less than the size, and an I plus plus. And afterward, we want to print out without the line. We're going to print out the I, and then plus, we're going to add the arrow. Or not I arrow, just an arrow. And afterward, inside of that, we want to write out, we want to call it, let's write out integer, and we're going to call it neighbor. And for that, we're going to get the I of the neighbor. So then now we print out the neighbor. Okay, oh, let's also make sure there's space in it. Then afterward, you want to print out line for spaces. Okay, now let's have the public static void in the, we're gonna have our main here. Okay, so integer, we're gonna call it v. We're gonna have it like, let's say 5. Now we're gonna create the whatchamacallit, the adjacency list. So list integer. I'm gonna have it equal to the new array list. Oops, like that. For, again, integer I to 0, I is less than v, then I plus plus. Oops. We're gonna add, yep, then new array list, like that. And now we're basically done. Now we can just start getting some examples, right? So add edge. Gonna have let's give it some values, right? Like 0, 1. We're gonna do, let's do the same thing as before. We have the 0, 1, 0 points at 4. Start pasting down a couple of them real quick. We have 1 here, 1 here, 1 here, and then 2, and then 3. What else was the 1 with? 1 was with, 1 was with basically everything. So 2, 3, 4, and then 2 touches 3, 3 touches 4, yeah? Or 3 touches 4. Okay, now all of that is done. We're gonna then print out the graph. And then let's run it. Perfect. Boom. That's how it's done. Okay, so let me double check if everything's correct. Yep. Okay, cool. Yeah. Okay, so what we have here, first things first, I just wrote this because I want to just basically import the Java utility classes like we need, like list, array list, and stuff like that. Now for this, so what we have here is basically, so for this part, it's just a function to add an edge between the nodes U and V. ADJ is for the adjacency list. All right, and then for these two, okay, what we have here, let me go with the first one. So the first one is basically it goes to node U's list, right? And then add V as a neighbor. So what we do is we get the U from the list and then we add the V as its neighbor. And because, like I mentioned, this is an undirected graph, you want to do the same thing on the other side where you grab the V and then add the U. Just keep in mind, we have to add the reverse connections because this is undirected. And that's basically the end of the add edge. So just keep that in mind. Now for here, this is the part where we basically print the adjacency list in a way that's readable, right? And that's why I have it like this. So for the first part on the for loop, what I want to do is we're going to loop through every node I from 0 to V minus 1. And then by the way, the V would just be, would be this one right here, okay? This V, this capital V. So if I increase this to 6, it would be 0 to 6. Minus 1, which is 5, but you know. Okay, so, and then we have the adjacency list size, which is going to be equal to the number of the vertices V. Afterward, we want to print out the number list, right? And that's why we have the arrow right here. So it's going to be I, which is 0, and then 1, and then 2, 3, 4, but with an arrow attached to it. And then here is basically where we print out like all the neighbors. So for the current node I, we want to loop through all of its neighbor. So the neighbors would be these right here. As you can see, 1, 4, 2, 3, 4, 3, 4, all of these. And just by looking at it, you can kind of see it. Let's say we have through our U, right? We're on our U right now, which is 0. So for here, we create an integer that's called neighbor. And what it's gonna do, it's gonna get the adjacency list and get the I, right? So the neighbor's right here. So we want to print out the neighbor, and it'll print out 1 and then 4 with a space, 1 space and then 4. And then once the 0 is done, then we print out a space and then continue forward to the next one, which is 1. And for 1, again, it's going to go loop through and print out all the neighbors. So it'll be 0, 2, 3, and 4. And then it's going to do the same thing. And it repeats, right? So that's how basically it works. And on the main function, which is down here, what we have, again, number for integer v equals 5, that just means the number of vertices is 5. So we need nodes like 0, 1, 2, 3, 4. Now for this part, this is the part where we create the adjacency list container. This will hold basically like the v list, one list per node. And then for here, this is basically we're creating the v empty list, right? And then after this, the structure would look something like, basically looks kind of like this. And 3 and 4, like this, right? That's the structure. It's basically everything is empty from 0 to 4. In order for us to have numbers in there, we have to do the add edges. And that's how we were able to add all of these numbers into the empty list. And then afterward, you print out the graph. So that's how you do it. Hopefully it makes sense. I mean, if you type it out yourself, you know, you'll be able to understand it too. So, all right, let's talk about the complexity, because that is what we're gonna end up with. We're gonna end this with a very nice complexity. Now, keep in mind, we're gonna have v. V is the number of vertices, just like right here. Or nodes, you can call it nodes, vertice or nodes. And then let's also have e, right? E is what you call number of edges. And so when we build adjacency list, it will basically be, when we're building the adjacency list, right? It will basically be big O of v plus e. Okay? And so keep in mind, the v is to create the empty list, while the E is to insert edges. So, you know, that's what you would say for the space complexity. It would just be big O of V plus E, like that. And that's it. So for this video, it'll just be on the very basic of what a graph is, and as well as talking about the undirected graph. Next video, I'll be talking about the directed graph. So it'll be a little bit different, but similar ways to think. Anyway, thanks for watching. Bye.